Swayam Prabha. Digital India. Educated India.
Welcome to the lecture series on tutorials on design of transmission elements. In this lecture series, we will study different tutorials on different transmission elements. And this lecture series presumes that you have already studied the design of transmission elements. The first lecture on this lecture series is the tutorials on basics and force analysis of the spur gears. And we are going to take a problem related to basics of the spur gear. The problem is a gear set consists of a 16-tooth pinion driving a 40-tooth gear. The module is 12 mm. Addendum and dedendum are 1 times module and 1.25 times the module respectively. The gears are cut using a pressure angle of 20 degree. So, in this problem we have to find first compute the circular pitch, the center distance and the radii of the base circles. And B part of this question is, in mounting these gears, the center distance was incorrectly made 6.0 mm larger. Compute the new values of the pressure angle and the pitch circle diameter. It means when the gear was mounted, then the center distance, which is this one, this is the center distance C, which is equal to the pitch circle radius of the gear, which is dg divided by 2 is the pitch circle radius of the gear plus pitch circle radius of the pinion, which is dp divided by 2. So, dp divided by 2. So, we have to find the center distance, and the center distance was incorrectly made 6 mm longer. So, the new center distance will be this one, and due to this change in center distance, the pressure angle changes, and we have to find that changed or the new value of the pressure angle and the pitch circle diameters, because with the change in center distance, the pitch circle diameters will also change. Now, in this problem we have been given the number of teeth on the pinion. So, Zp is 16, number of teeth on the gear is 40, so Zg is 40, module is given as 12, and we know module is equal to the pitch diameter d divided by number of teeth. So, d divided by z is given. The addendum is standard 1 module. So, HA is the addendum, which is 1 module, and dedendum is 1.25 times module. So, it is given HF is equal to 1.25 m, and the change in center distance is given as 6 mm. Now, let us solve this problem. In this figure, different nomenclatures of the gear tooth are given, and in that the circular pitch is the distance between the 2 points, 2 consecutive points along the pitch circle. So, this is the pitch circle. Along the pitch circle, the 2 consecutive points are this one. This is on the one gear and one gear tooth, and this is on another gear tooth, So, this distance is your circular pitch, and circular pitch is given by pi multiplied by module. So, module is given as 12, and so circular pitch will be pi multiplied by 12, which is 37.699 mm. The pitch diameter of pinion and gear are respectively, from the definition of module, which is m is equal to pitch diameter divided by number of teeth. So, pitch diameter d will be given by m multiplied by z, m multiplied by z. So, to get the pitch circle diameter of pinion dp, m will be multiplied by number of teeth on the pinion zp. This is your zp. Zp is 16, number of teeth on the pinion is 16. So, 16 multiplied by 12 is 192, it is the pitch circle diameter of the pinion. Similarly, pitch circle diameter of the gear is number of teeth on the gear, which is 40, times module, which is 12, which is equal to 480 mm. And thus, we determine the pitch circle diameter of the pinion and pitch circle diameter of the gear. This is the center of the pinion. O1 is center of rotation of the pinion, about which the pinion is rotating, and O2 is the center of rotation of the gear, and distance between this O1 and O2 is the center distance, and this is given by C is equal to pitch circle radius of the pinion, this distance, this is equal to d pinion divided by 2, and this is the pitch circle radius of the gear, which is pitch circle diameter of the gear is dg divided by 2. So, dg divided by 2 plus dp divided by 2 is the center distance, and we obtained it as 336 mm. Since the teeth are cut on a 20-degree pressure angle, in the problem, pressure angle was given as 20 degree, and we know that the pressure angle is the common tangent on the base circles. So, this is the base circle of the pinion, and this one is the base circle of the gear. Involute profile starts from the base circle, and a common tangent on the base circles is CD, this. CD is the common tangent on the base circles, and angle made by common tangent on the base circle and common tangent on the pitch circles. Pitch circle of the pinion is this one, this is the pitch circle of the pinion, and pitch circle of the gear is this one. And common tangent on the pitch circles of the pinion and gear is this A and B. Thus, the angle between these two, that means AB and CD, is the pressure angle, and this pressure angle is given as 20 degree in our case. Therefore, the base circle radius, which is, this was the base circle, and the base circle radius is this one. Now, the base circle radius is given by, as we know that this CD is tangent on the base circle, and so this O1 and this point, let this point is capital A. So, O1 capital A is perpendicular to CD, and O1P is equal to pitch circle radius, and the angle AO1P will equal to the pressure angle, because this angle is CPA is pressure angle phi, and so angle AO1P will equal to pressure angle phi. Now, from the triangle O1AP, we can find the base circle radius of the pinion RB1 is equal to dP divided by 2 and cos of the phi, dP divided by 2 cos of the phi, and which is written here. The base circle and pitch circle radiuses are related with the help of the pressure angle, and base circle radius is equal to pitch circle radius multiplied by cos of the phi, and so base circle radius of the pinion is equal to the pitch circle radius of the pinion, which is 192 divided by 2 cos of the phi, that is 90.210, and base circle radius of the gear is equal to pitch circle radius of the gear, which is 480 divided by 2 cos of the phi, which is 225.526 mm. Now, let us find the effect of change in center distance. The first figure shows the case in which the center distance is this O1, O2, and the corresponding pressure angle is 20 degree. This is the angle between common tangent on the base circle and common tangent on the pitch circles. This is 20 degree. Now, the center distance slightly changed during the mounting, and this change is 6 mm. So, earlier center distance was C, now it becomes the new center distance is equal to old center distance, new center distance C dash is equal to old center distance plus 6 mm. Due to that, what happens is the base circle will remain unchanged, because involute tooth profile is generated from the base circle, so it will not change. The pitch circles will change because the center distance is changed, and this center distance, change center distance, will equal to the new pitch circle diameter divided by 2 plus new pitch circle diameter of the gear divided by 2. This will equal to C dash, and this C dash is equal to C old center distance plus 6. Now, due to change in pitch circle diameters, the common tangent on the pitch circles will change its location, and due to that the pressure angle will change. So, let us find the way the new pressure angle is determined. Designating dP dash and dG dash as new pitch circle diameters when the center distance is increased by 6 mm. The new center distance C dash is equal to C plus 6 mm, and that is equal to new pitch circle diameter plus of the pinion plus pitch circle diameter of the gear divided by 2, and that is equal to 342 mm. earlier the center distance was 336. C was 336 mm. Now it is 342. It has increased by 6 mm. Now the property of involute tooth profile is, with the slight change in center distance, it remains satisfying the fundamental law of gearing. It means the velocity ratio will remain unchanged. Now when the velocity ratio is remaining unchanged, it means new pitch circle diameter of the pinion divided by new pitch circle diameter of the gear is equal to earlier the velocity ratio. The earlier velocity ratio was number of teeth on the pinion was 16, number of teeth on the gear was 40. This is actually number of teeth on the pinion, number of teeth on the gear, which will remain unchanged. And so the velocity ratio will remain unchanged, and it will remain as 16 divided by 40. Now solving A and B, we will get the new pitch circle diameter of the pinion and new pitch circle diameter of the gear. The base circle will remain unchanged, and this R is changed, and this will remain unchanged. This has changed, and so this phi will change to make it unchanged. The base circle will remain same as the gear teeth were formed on that. The new pressure angle is obtained as RB, the base circle radius, is equal to pitch circle radius multiplied by cos phi, which is equal to 90.210 for the case of earlier one, and that should equal to the new pitch circle radius divided by multiplied by cos of the new pressure angle, and that is 195.429 divided by 2, which is Rp dash. Rp dash is equal to 195.429 divided by 2 cos of the phi dash, and so phi dash is equal to cos inverse 90.212, which is equal to Rb, divided by 195.429 divided by 2, and thus the new pressure angle is 22.60. So new pressure angle is 22.6 degree. So with the change in center distance, the pressure angle changed from 20 degree to 22.6 degree, but it will continue to satisfy the fundamental law of gearing, and thus velocity ratio will remain unchanged. Now let us take the second problem, which is related to force analysis of the spur gear. That means when power is transmitted from one gear to another gear, then how force, what type of forces acts and how force is transmitted. So in this problem, pinion 2, this is the pinion, runs at 1750 revolution per minute and transmits 2.5 kilowatt to the idler gear 3. This is the gear which is nomenclated as third gear, and it is an idler. Idler means it will not transmit power to its shaft. It will just transmit power from this pinion to this gear, and the advantage of this idler will be the direction of rotation of the pinion and gear will be same. If it is rotating in an anti-clockwise direction, and so this will also rotate in an anti-clockwise direction, and thus if A is the driving shaft and C is the driven shaft, both the shaft will rotate in same direction. But if an idler will not be there, then the pinion direction of rotation of the gear will be opposite to the direction of rotation of the gear. If pinion is rotating in anti-clockwise direction, then the gear will rotate in clockwise direction. For the case of external gear, in the case of internal gear, it will be just opposite. So, the teeth are cut on 20-degree full depth system. It means pressure angle is 20 degree, and gear tooth are such that they are standard gear tooth, which is called the full depth, where addendum will equal to 1 times module and dedendum will equal to 1.25 times module. It is called the full depth system, and have a module of 2.5 mm. Draw free body diagram of gear 3 and show the forces that act upon it. This is the pinion and this is the gear, and the pinion is rotating in the clockwise direction with the speed n2, then it will apply force along the pressure line. Pressure line is common tangent on the base circle, and this line is common tangent on the pitch circles, and so the angle between this is called the pressure angle. So, force from pinion, the driving gear, to the driven gear is applied along the pressure line, and so this is also called the line of action. If we draw the free body diagram of pinion, then on the pinion a force will be applied by the gear, which is the third member, along the line of action with an angle equal to pressure angle, and at the shaft opposite force equal to Fa2 will act. Now, for the gear, the free body diagram is shown, and in this free body diagram the force on the gear, which is a driven member, and this is the driving member. On the driven member, this pinion, the driving member, will apply force in the direction of line of action with angle equal to phi with the tangent on the pitch circle of the gear. This is the pitch point P, this is the pitch point P, this is the pitch point P. The pressure line. The force on the shaft B will act opposite to this force F23. F23 is the force applied on third member by the second member. F32 is force applied on second member by the third member. Second member is the pinion, third member is the gear. Now, this methodology is used in the given problem, and this is the free body diagram of the idler. The power H transmitted through a rotating gear can be obtained from the standard relationship of the product of torque and the angular velocity. That means the transmitted load is equal to this F32 transmitted, which is a component of the force applied by third member on the second member. This is the second member, and which is idler. So, transmitted load is F32 transmitted, and it can be obtained from the power which you are going to transmit and the pitch line velocity. So, H is equal to Wt multiplied by pitch line velocity, and the pitch line velocity is equal to pi pitch circle diameter multiplied by rotational speed in RPM divided by 6000. So, this is your pitch line velocity multiplied by Wt is equal to the power which you want to transmit. So, from this we will get the value of Wt. Now, this was our problem. This is the pinion, this is gear, pinion and the idler, and this is gear. And this is the free body diagram of the idler. At this point, the pinion is transmitting power to the idler, and at this pitch point, the idler is transmitting power to the gear. So, there are two pitch points for the case of an idler. At this pitch point, we may say it as P1. The force applied by the pinion will be in this direction. This will be the pressure line. Well, this is your F23. Force applied on third by the second member. Okay, this will be for the case of idler. So, this is your F23, and the component of these in the tangential direction to the pitch circle will be the tangential force, and that will be the transmitted force. And this force has a component along the radial direction towards the center of rotation of the gear or this idler, and that is the radial component. And so, the normal component, normal force, this is the normal force which is acting at this pitch point on the idler will have two components. One will be the tangential component, which is F23 tangential, and another will be the radial component, F23 radial. At this pitch point, which is P2, what will happen is, now the idler will become the driving member, and this will become the driven member. Here the pinion is at P1, pinion is driving and gear not idler, idler is driven member. But for the case of P2, your idler will become the driving member and gear is driven member. The direction of rotation of the idler for this P1 is this one, and so the transmitted load will act in the direction of rotation of the idler. The rule is, if the gear is driving member, then tangential force acts opposite to the direction of rotation. For the case of driving member, and for the case of driven member, tangential force, your tangential force, the force component tangent to the pitch circle, force acts in the direction of rotation. Now, at the pitch point P1, the idler is the driven member and pinion is driving member. Okay. And so, tangential force will act in the direction of rotation. Direction of rotation is shown by the red arrow, and so the tangential force will act in the direction of rotation of the idler. And the radial component is shown here. Radial component will always act towards the center of rotation, and so this will be in this way. Now, for pitch point P2, idler is driving member, and thus the transmitted load will act opposite to the direction. Direction of rotation is shown by this arrow, and thus opposite to the direction of rotation the tangential force will act, and this tangential force is a component of normal force F43, which is applied by fourth member on the third gear. Third one is the idler. So, this is actually Wn, the normal force. The component of this normal force is this tangential force, and it will act opposite to the direction of rotation. And the radial component will always act in the along the axis of rotation. The pitch diameters of gears 2 and 3, gear 2 and gear 3 are D2, the pitch circle diameter of the pinion or the gear 2 is equal to number of teeth on the second gear, this second gear, multiplied by module, and that is equal to 50 mm. Similarly, D3, pitch circle diameter of the third member, that is which is the idler, is equal to number of teeth on the idler multiplied by module, which is 125 mm. Now, pitch line velocity is obtained as pitch line velocity V is given by pi d2 pitch circle diameter of the pinion multiplied by RPS revolution per second of the this pinion, the second member, divided by 60 when d is in mm. Substituting the values, d2 is 50 mm, the RPM of the pinion is 1750, this is RPM, and so it is divided by 60 to get our revolution per second multiplied by 100 is your, if this is in mm, then it will be divided by 1000, and so the pitch line velocity is 4.58 meter per second. This is the pitch line velocity along this pitch. So, the transmitted load will equal to the power which you want to transmit from this pinion to the idler, which is equal to 2500 watt divided by, it is given in the problem, divided by pitch line velocity, and so the transmitted load is obtained here at this point. This is the transmitted load at this point. So, we have this F23 is given by this one. Thus, the tangential force on the gear 3 F23 tangential is equal to 546 Newton. Now, the radial component is equal to F23 radial, this F23 radial is equal to F23 tangential multiplied by tan of the phi, phi is 20 degree, and so it is 199 Newton. This is 199 Newton and this is 546 Newton. And so, F23, which is the resultant force of the tangential and the radial, which is also called the normal component which is equal to 581 Newton. Since gear 3 is an idler, it transmits no power to its shaft, and so the tangential reaction on gear 4 on gear 3 is also Wt is equal to 546 Newton. Therefore, F43 tangential is equal to 546 Newton, 546 Newton. F43 radial is 199 and F43 radial is this one, and F43 is 581. Here the forces are shown here. The shaft reaction in the x and y direction is shown here. In the total shaft reaction is FB3 on the idler, and its component along the y is FB3y, and along the x is FB3x. Now, summation of forces along the x direction should be 0 for this free body diagram, and the forces which are acting along the x direction is F43 radial and F23 tangential and FB3x. So, F43 radial plus FB3x, because both are in same direction, minus F23 tangential is equal to 0, and from here, from this equation we got the FB3 in the direction of x. The bearing reaction in the direction of x is equal to 347 Newton. Summation of forces in the y direction should also be 0, static equilibrium equation, and applying that, the forces which are acting in this free body diagram in the y direction are, the forces are, this is acting in the y direction, this is acting in the y direction, and this one. The direction of this and this is same, and this is acting in the opposite direction, which is shown here, and from that we get the shaft reaction in the direction of B in the direction of y, and that is given by 347 Newton. And thus we got on the idler the forces which are acting at pitch point P1, forces which are acting at pitch point P2, and the shaft reaction at B. Now, next take the third problem, which is given as a 21 teeth gear has 20-degree full depth involute teeth with a module of 12 mm. Calculate the radii of pitch circle, base circle, addendum circle. Determine the tooth thicknesses at base circle, pitch circle, and addendum circle. That means, if a gear tooth is like this is your addendum circle, this is your pitch circle, and this is your base circle. So, we have to find tooth thickness at the base, which is TB, tooth thickness at the pitch circle, which is TP, this is your tooth thickness, and the tooth thickness at the addendum, which is TA. This we have to find. Given our number of teeth are 21, pressure angle is 20 degree, module is 12 mm. So, from the module we got the pitch circle diameter of the pinion, which is module multiplied by number of teeth. Pitch circle radius of the pinion is 0.5 of the mz, and that is 0.5 multiplied by module multiplied by number of teeth, which is equal to 126 mm. Base circle radius RB is given by pitch circle radius multiplied by cos of the pressure angle. Here we have taken pressure angle in terms of alpha, and so the pitch circle radius of the pinion is given by 126 multiplied by cos of the pressure angle is 118 mm. So, base circle radius is 118.4 mm, pitch circle radius is 126 mm. and thus this is the base circle, this is the pitch circle, and this one is the addendum circle. Addendum circle will equal to addendum circle radius will equal to the pitch circle radius plus the height of the gear above pitch circle is addendum. Therefore, addendum circle radius is equal to the pitch circle radius plus addendum, which is HA. So, RP plus HA will be the addendum circle radius. Addendum is 1 times module. So, addendum circle radius is pitch circle radius plus addendum. Addendum is actually this one. If this is the pitch circle and this is your addendum circle, so this is called the addendum, and which is equal to 1 times module. So, circular pitch PC, the distance between two consecutive gear tooth, so distance from this to this along the pitch circle is called the circular pitch, and which is equal to pi multiplied by module, which is 37.14 mm. The thickness of gear tooth is defined along the pitch circle. Along the pitch circle, thickness of the gear tooth is defined. So, if we are saying thickness of the gear tooth, then it will be thickness along the pitch circle, and that you may say TP. TP is actually thickness of the gear tooth, and we know that this will be half of the circular pitch. This complete is along the pitch circle. This is your pitch circle, is the circular pitch pi multiplied by m, and this one, this is thickness of the gear tooth TP. So, TP is half of the circular pitch, and circular pitch is 37.14, and so it is 18.57 mm TP. Now, to determine the gear tooth thickness, we are going to use the concept of involutometry. Involutometry, which is obtained from this figure. Let this is the center of rotation of a gear, and this circle is the base circle, and from the base circle involute tooth profile is generated by rolling this line or this scale along the base circle without slipping. So, originally this P point was at S. Now, when the ruler was rolled, then the traced line is curve SP, and this is your involute. So, at any point, if P is a point on the involute, then from this P, if a tangent is drawn, then that tangent is at T, capital T, and so this PT is the generating line. This line is generating the involute tooth profile. So, from the tangent point T, a line is drawn to the center of rotation G, and this P is connected to the G with a line PG. So, if the angle PGT is equal to alpha, which is the pressure angle, if this is along the pitch circle, if this P is along the pitch circle. This is the pitch circle. Or in general, you may say that any general point is there and the angle PGT is alpha, and an angle PGS, the point where involute tooth profile has generated or involute tooth profile was generated from the base circle, and S is on the base circle. So, the angle PGS is phi. So, ST, arc ST is equal to line PT, because your roller was earlier tangent to this one like this. This was your ST and it has moved in this way, and at present time this T is at this location. So, this PT is equal to arc ST. So, arc ST is equal to TP, and ST, arc ST is your RB, base circle radius, multiplied by this angle. This angle is phi plus alpha. So, arc ST is equal to RB multiplied by phi plus alpha, and so TP is equal to RB phi plus alpha, and TP may also be obtained from triangle GTP. From this triangle, your PT is equal to RB, this is RB, GT is RB, and tan of the alpha. And so, we have a relationship phi is equal to tan alpha minus alpha. That means, you may write it as RB phi plus alpha is equal to RB tan alpha. So, from this relationship, this RB and RB is cancelled. So, phi is equal to tan alpha minus alpha. That means, the angle between a point from where a tangent is drawn on the base circle and start point, this angle is given by tan of this minus this angle. This is called the involutometry, and this methodology is used to determine the gear tooth thickness. Similarly, the thickness of the gear tooth at the pitch circle, this is the pitch circle represented here, pitch circle. So, that is capital P to P dash. So, P dash is the tooth thickness along the pitch circle, and that is written as TP, and it is equal to the angle this PGS or G1, this angle, and twice. So, 2 times angle G1 GP is equal to PP dash, and the GP is the pitch circle radius, and so the gear tooth thickness at pitch circle is 2 times angle G1 GP multiplied by RP, which is the pitch circle diameter of the gear. So, angle G1 GP is written as beta, and that beta is equal to, so this angle is beta, angle G1 GP, this one is beta, and that is equal to this PS divided by GP, which is R or RP, the pitch circle radius. and so beta is equal to Tp divided by 2, which is Ps, and divided by Rp, and angle PGPO, PGPO, this angle PGPO, let me make it highlighter, angle PGPO is equal to angle PGB, PGB minus POGB. Well, and that is equal to phi, this angle phi, this one from this to this, minus phi 0. Also angle PGPO, PGPO is equal to angle G1 GPO minus angle G1 GP, and so that is beta 0 minus beta. And now from the involutometry we know that angle phi is involute alpha, and that is equal to tan alpha minus alpha. Similarly, we know that the phi 0, this phi 0, this one is equal to involute phi alpha 0, and that is tan alpha 0 minus alpha 0. Therefore, beta 0 minus beta is equal to alpha minus alpha 0. Now, this beta 0 minus beta is T 0 divided by 2 R 0, and this beta is Tp divided by 2 Rp, and this one is involute of the alpha, and this is involute of the alpha 0. And so, we can write TO. TO is the thickness of the gear tooth at a radial distance of r, and Tp is the thickness of gear tooth along the pitch circle divided by 2 Rp, pitch circle radius, is equal to involute of the alpha minus involute of the alpha 0. Now, knowing this equation, now the thickness of the gear tooth at a radial distance of r 0, any radial distance of r 0, this G P 0 is a radial distance r 0, okay, can be determined, and that T 0 is this P 0 dash, this distance, this is T 0, gear tooth thickness at a radial distance of r is equal to 2 r 0, the radial distance, this r 0, within the bracket Tp divided by 2 Rp plus involute alpha minus involute alpha 0. The P 0 is now, we want to determine tooth thickness at the base circle. So, the radial distance of P 0 will become the radial distance of the base point, which is S. So, P 0 will shift to P 0. This P 0 will shift to S, and from S we will draw a tangent on the base circle. So, P 0 is now at B, and P 0 T 0, this P 0 and T 0 is the tangent at B. So, T 0 is T B, the gear tooth thickness at the base circle, and RO, the radial distance of P 0, will become the RB, the base circle radius, and alpha 0 will become 0, because at B, when we will draw a tangent, that will be not touching the base circle at any other place. So, TB, the gear tooth thickness at the base circle, along the base circle, means this distance, radial distance, is equal to 2 RB, the base circle radius, within the bracket Tp, the gear tooth thickness at the pitch circle divided by 2 pitch circle radius plus involute of the alpha minus involute of the alpha 0. So, the pressure angle is 20 degree, and so involute of the alpha is given by this one 0.015, and alpha 0 is this alpha 0 is 0, and so substituting these values we got the gear tooth thickness at the base circle, which is 21 mm. Similarly, we can find the tooth thickness at the addendum circle. This is the addendum circle represented here. So, along the addendum circle we want to find the gear tooth thickness. So, this P0 point will shift to A, and from A tangent will be drawn on the base circle, and gear tooth thickness along the addendum is TA. So, from A tangent is drawn on the base circle, it is touching the base circle at TA, and TA is joined to G. And this angle TA G A is alpha A. So, cos of the alpha A is G T A divided by G A. This is 90 degree, this is 90 degree. And so, we got alpha A, this angle, the TA G A, this angle is 0.54 radian. So, involute of the alpha A is tan alpha A minus alpha A, and substituting the value of alpha A, we got involute of the alpha A as 0.059. Now, we want to find the gear tooth thickness at addendum. So, this TO will become TA, RO will become the radial distance of the addendum circle from the center of rotation, and so it is GA, and that is RA. So, this RO will become RA, and alpha will remain same, and this alpha 0 will become alpha A. Substituting all these, we get the tooth thickness along the addendum, and that is 8.20 mm. Now, as per standard, it is said that minimum gear tooth thickness at the addendum is equal to 0.25 times the module, and that is equal to 3 mm, and our gear tooth thickness is 8.2. So, our addendum is gear tooth thickness along the addendum is more than the allowed minimum thickness at addendum circle, and so gear tooth thickness is correct. So, TA is greater than TA minimum. Now, from all these analysis of stresses, what we got that on the gear tooth, two type of forces acts. One is the bending stress, and therefore, gear tooth may fail due to fluctuating bending stresses at the root of the gear tooth. That means, a gear tooth is something like this, and the tangential force is acting in this way, and the normal force is acting in this way. So, this tangential force will bend the gear tooth, and so at the root bending stresses will act, and these bending stresses are fluctuating in nature, because when the gear tooth will come in contact, the bending stresses will develop, and when it will disengage, then it will become 0. So, fluctuating bending stresses acts on the gear tooth. Similarly, the two gear tooth, when they are transmitting the power, then they are in contact, and at the contact point, at this contact point, very high contact stresses develops, and these contact stresses are also of fluctuating nature, because they will act when there will be engagement of the gear tooth, and they will become 0 when there will no engagement. So, after getting the stresses, we determined the strength under bending and strength under surface contact stresses. And the ferrous material have bending endurance limit, we know, and materials do not exhibit an endurance limit for repeated surface contact stresses. In designing, we have to ascertain whether the design component will work satisfactorily or not, and for that adequate assessment or adequacy assessment is made. That is, a specification set for a gear mesh includes the following: gear, what will be the material, what will be its core, core means inside the gear tooth, inside core, what is its hardness, and along the surface which will resist the surface stresses, what is the hardness. So, material, core and case hardness is very important, and the service description includes the power which we want to transmit, at what speed, what will be the overload factor, what will be the reliability required, and what will be the life required, what are the mounting methodologies, and the face width, this face width which is recommended as 3 pi times module to 5 pi times module. So, and the design objectives will be the resulting drive should be compact and small, operate smoothly and quietly, have long life, be low in cost, be easy to manufacture, be compatible with the other elements in the machine elements such as bearings which are used in the support of the shaft itself which is required to be transmit the power from this shaft to this shaft, then the housing in which the gears are kept or the gearbox is kept, then the driver and the driven machine. What is the driving machine? What is the driven machine? So, in this figure, the complete description is shown, and with this we have to design the gear tooth or the gear. With this, the first lecture of the tutorial on design of transmission elements, which was tutorials on basics and force analysis of spur gears, is completed. In our next class, we will solve some problems related to design of spur gears. Thank you.